wait a few seconds here to allow people to connect, and then we'll get started. Okay, well, hello everyone. Good morning, good afternoon. I'm Renee Yager. I'm the Director of Marketing at EPC, and welcome to today's webinar, Design Tips to Maximize the Performance of GaN-Based Designs. This is the first of our 4-part summer series, which is running bi-weekly through the beginning of September. Recordings will be available after each webinar, so please remember to register even if you are unable to attend the next ones live. The full schedule and details are available on the website at epc-co.com. Before we get started, just a few housekeeping items. You will have the opportunity to submit text questions to the panel by typing your questions into the Q&A function at the bottom of the screen. You may send in your questions at any time. We'll collect these and address them during the Q&A session at the end of today's presentation. So now I would like to introduce our speaker today. Brian Miller joined EPC in 2016, where he is the Field Applications Engineer for the Eastern North America. He has over 30 years of experience in power electronics as a design engineer and as a field application engineer. At IBM and Sony Ericsson, he designed small, efficient power supplies and battery chargers for laptops, tablets, and other equipment, and designed a custom analog controller IC for laptop DC-DC and battery charging. Previous to EPC, Brian was a field application engineer for Semtech, where he is involved in designs for AC-DC, DC-DC, LED lighting, and other areas. He has authored patents, articles, and talks. Brian received his MSc and BS degrees from Duke University. Brian, thank you so much for joining us today.
Thank you, Renee, and welcome everybody. Thanks for joining today for the summer series, Design Tips to Maximize the Performance of GaN-Based Designs. Let's jump right in, and as Renee said, there'll be time for questions afterwards. And even if there aren't, if you think of a question later, just feel free to write me in person or write into EPC. So for today, we'll cover things like the GaN technology review, driving GaN FETs, layout, thermals, including adding heat sinks to GaN devices, to cover some of the major topics that happen with GaN-based designs. So first, a review of GaN FET characteristics. There's some key metrics with GaN FETs. Reverse recovery, there isn't any, which is great. Reverse conduction, which is a little bit different than silicon MOSFETs. Switching characteristics, the Miller ratio, and also reliability. Jump right into performance metrics. Over here we have the RDS-on. This is the measure of the size. You can see here the ideal size would be down the lower right-hand corner, a real high breakdown with very low resistance. So moving up, you see over here the silicon MOSFET theoretical limit is right here. As of 2010, EPC GaN FETs were already noticeably better than the theoretical limit of the silicon MOSFETs. And today that line has moved a little bit closer here. You can see in blue, the theoretical limit is way out here. So there still is room for further improvements in GaN FETs. First, recovery. On the left here, you'll see a silicon MOSFET. You'll see various dead times, 5 nanoseconds, 20, 40, in different colors here. And you can see the ringing and how the ringing changes as you have different dead times, which implies that the ringing is at least partially responsible due to the dead time. On the right-hand side, you'll see a GaN FET which has no reverse recovery, and you'll see the noticeably less ringing on the switch node. And both of these have, at the bottom, 48 volts in, 12 volts out, 20 amps, and 500 kilohertz. Reverse conduction. Even though GaN FETs do not have a parasitic PN diode, they still conduct very well in the reverse direction through the main channel. Here's a graph. You'll see these are two different temperatures, 25 degrees C blue, 125 degrees C in red. Yes, the voltage is higher than MOSFETs. It behaves like a diode, but it's easy to manage. The dead time, because there's no reverse recovery, the dead time can be very small. And there might be times when you want an anti-parallel diode, but there's also better ways of doing that in many power supplies, which we'll get into. Okay, switching characteristics. As it says here, GaN FETs switch much faster than MOSFETs. And as the voltage goes up, you'll see the benefit increasing about 5 times or more at 100 volts and about 10 times or more at 200 volts. So the figure of merit here is the charge on the gate times the resistance. And you'll see the blue dots are various silicon MOSFETs. The green dots are EPC GaN FETs. And you'll see the light green, older ones, and the darker colors today. And you can expect that line to continue to go down to improve as time goes on. Okay, Miller ratio. You'd like to have the FETs switch very fast, but not switch themselves on. In other words, you want a high dVdt immunity, so nice fast edges without having the issue of the dVdt turning back on the gate. One very nice thing about the EPC GaN FETs in green, if you look, they're all below the number 1, the Miller ratio of 1, which means that you don't have to worry about this high dVdt switching on the GaN FETs when you don't want them to come on. There's quite a variation in silicon MOSFETs, but it was designed by intention by EPC to help this. So you could say, even though GaN FETs have very high switching, they can have very high dVdt. That does not cause the problem of causing the gate to bounce up and to turn back on when you don't want. Okay, the next section, that concludes the first part of just a review. Now designing with the GaN FETs. Some topics here are gate drivers, layout, thermals, and again, adding heatsink. GaN FET gate drivers. The basic idea is very simple. It works like 5-volt logic. 5 volts is on, 0 volts is off. That's the EPC GaN FET in a nutshell. Now, to optimize it, there are some things to keep in mind, some design considerations. We'll go through some of those. This is the typical gate driver here with a PWM signal, the VDD, which is typically 5 volts, and a resistor. That's typically all that's needed, just a resistor between the gate driver and the gate of the GaN FET. We'll go through driving requirements, protection features, timing requirements, GaN-specific requirements, all these to optimize the operation of the switching. Okay, first let's cover dead time and reverse conduction. As you saw before, there is reverse conduction, but the voltage is a little bit high. So on the positive side, you don't have the reverse recovery, so you don't have to worry about that, but you don't want to spend a lot of time and dead time just because of the voltage in the reverse direction. Estimate about 2.5 volts. It's, because of that 2.5 volts, that means that this point, the switch node can be minus 2.5 volts. And then going through a charge pump, you have to make sure this doesn't charge pump up too high. So a typical GaN half-bridge gate driver will have a regulation limitation method on the top, just to keep this at a typical 5 volts. Also, the driver must work with negative switch mode voltage up to 5 volts, just to make sure everything's okay. DVDT capability. Now, we've looked before at the DVDT capability of the GaN FETs, but this is with respect to the driver. The GaN FETs switch very fast, and you can have some half-bridge gate drivers that have to withstand this. Especially isolated drivers seem to be something to to look for. And there are some that are rated for very high dV/dt. Drivers should be rated for greater than 100 kilovolts per microsecond, or to put another way, 100 volts per nanosecond. Here's an example waveform with one of EPC's Gen 5, one of our newer FETs, showing 73 kilovolts per microsecond. So this isn't just a theoretical, you really can switch these very fast. Higher voltage rated GaN FETs switch faster, more voltage in the same time, obviously. Increasing gate resistances reduces dV/dt. So you could say, well, I can just slow down the FET, but you have an efficiency penalty. With good layout and other good practices, there might not be a reason to slow down the GaN FET. So to have a gate driver that can withstand that is a nice feature. Okay, next, threshold voltage. So the GaN FETs do have a low threshold voltage in the range of, say, 0.7 to 1.5 volts. So you'd like to make sure that when the GaN FETs are off, they stay off. You notice the driver here still is very simple on both the top and the bottom. There's just a positive voltage, typically 5, and down to ground, which is 0. There's no negative voltage used in this, not needed, and it actually doesn't improve performance, actually decreases performance to put a negative gate drive voltage with an EPC GaN FET. So many drivers have two outputs, a pull up and a pull down, which is very nice because you can have individual gate resistors. You can set the rise time and the fall time independently with this type of strategy. Just to avoid the circuit below, single output gate drivers. Some just have a single output, which is fine. But if you do something like this, you notice there's a diode here that can cause a drop. So that can cut into your noise margin. So it's best not to do this. So a single resistor is best for a single output of a gate driver. Okay, next, how to make sure it doesn't ring too much. The maximum voltage is 6 volts rated for EPC's GaN FETs. You don't really want to go above that limit because they can affect long-term reliability. So here's a graph in the oscillogram showing a possibility of ringing up to 6 volts and down and up and so forth. But if you see this type of thing, the way to damp this, the best way is just use a resistor, just a simple series resistor to do this. One of the reasons for this is there is a common source inductance and there's gate capacitance. But in general, the resistor will dampen this. An equation for that here, for those who would like to go through the calculations, for the on resistors, putting the values into here, and keeping this, that'll minimize or optimize the waveform into the gate of the FET. Next, under voltage, a similar way, switching off from on to off, you can see ringing. Now, if it goes below 0, that's fine. It won't hurt the GaN FET. It could hurt performance a little bit, so it's not great, but it won't hurt the GaN FET. What's more of concern is this. Here's the threshold. You don't want a ringing to go above the threshold to have potentially a turn on or a leaking on of the GaN FET. So exactly the same equation used here can help you optimize that and stay below the threshold for as fast switching as possible without a danger of ringing up too high. Voltage lockout. You'd really rather not drive the FET into the active range. So for that reason, we recommend these kind of thresholds. 4 volts enable, 3.8 volts or so disable on the gate drivers, both upper and lower gate drivers. Again, just to make sure you're getting the most out of the FETs under all conditions. Propagation delay. This is not switching speed, the actual propagation delay from the input of the gate driver to the output. There's quite a range in some of these. should be matched. It's another thing. So you can have dead time controlled. You'd like a small dead time. So if they can be matched within 5 nanoseconds, that'll help you control to a nice short dead time. The maximum delay should be limited to about 50 nanoseconds. So again, here the blue shows the turn on of the controller. The green shows the output of the gate driver. So you'd like to have the turn on delay not too long. Pulse width. So you'd like to have a minimum on time. That's a lot of times that's specified by the gate driver. A minimum dead time will be passed. So you'd like to respect that so that if you have a short on time, it actually goes through to the FETs. And a minimum off time also. To give the gate driver, in this example, time for the bootstrap, this capacitor right here to charge up. Obviously, if the top FET stays on at 100%, this capacitor will run out and it won't charge up again. There's been a very nice collection of gate drivers that has been growing, especially in the last few years. There's really quite a good assortment. Single drivers is just a single input, single output to drive a single FET. There's more than shown here, but 3 key ones are from TI LMG 1020 and the 25. These are very fast and also very small. They're great for small sizes or when you need a very fast driver. Beyond power supplies, they're used in pulsing lasers and so forth. So they're very, very good drivers. There's others with or without LDOs integrated into them for 5-volt gate drive. More exciting is the half-bridge gate drivers. There's been quite a growth here. The first 3 are all pin compatible, board compatible. You can have one board design and use a TI one, a UPI one, and an MPS one, all in the same footprint. Next up, there's some automotive ones, which is nice for the automotive, not just automotive customers, but some designs that want automotive approval for further, further confidence in the design. Going up, there's 200 volts, 650 volts. These 2 have separate semi-floating bottom drivers, which is nice for current sense resistors. And the last 2 are isolated, which means you have quite a bit of isolation between the input and output. So for, say, offline power supplies or other things across the isolation barrier, these are very nice. There's additional gate drivers in development. There's also GaN controllers, power supply controllers in development, and there's 3 that have been released. 2 from Renesas ISL 81806, 807, which are dual buck and also dual boost. And so far, Analog Devices has released one advanced buck controller, which has a native GaN driver in it, which is LTC 7891. And again, there's more drivers and controllers coming. Question still comes up, okay? If you have a favorite driver, favorite controller, it looks like you can put a 5-volt driver out. Can you use that with GaN FETs? Do you have to have a specialized GaN FET controller and or driver? And in a lot of cases, you can adapt an existing made for silicon MOSFET driver controller to work well with GaN FETs. There's a few external parts you can add and a few things to check. So let's quickly go through that. First of all, the driver must use an external strap diode. You can maybe get away without, but it's really best. The reason is because you can put a current limiting resistor in series with it. Next, ensure the undervoltage lockout and operating voltage match a GaN gate. To make it really simple, can you do 5-volt gate drive and have a reasonable undervoltage lockout? Next, add measures to prevent bootstrap overcharging. So there's 3 here. A 5.2 volt Zener clamp, and this is a small signal one. There's not high current here. Let's see, that's over here on across not on the FET itself, but across the supply voltage for the upper gate driver. Also add a series current limit resistor, and that would be over here, which I mentioned before on the charging. And also down here, a Schottky diode. And that's to protect the switch node from going too far negative. Some controllers, some gate drivers can't take a very high negative voltage on that node. So this basic circuit has worked well for quite a few controllers out there. Things like 4-FET buck boost controllers, some battery charger controllers, other kinds of specialty controllers that don't yet have a GaN specific version. So feel free to contact us for information or discuss this point. Next, the layout. Okay, there's a lot here. We can go through that fairly quickly, but if you'd like to have an extended conversation, just feel free to contact us. First of all, parasitic inductance considerations. You'll see here, main one, the green boxes, is the common source inductance. That's both in the power loop, and it's also in the gate drive loop. That's something that can really cause problems for both of those loops, and it's really good to minimize that. And we'll show you how in a bit. Power loop inductance, the red dashed line, that's important to look at also. The gate loop inductance for both turn on and for turn off too. So just to look at the common source inductance, the one right here, what can that do? What difference does it make? Well, if you start with a 0 and you go up to even 1 nanohenry, which is not big, but 1 nanohenry here, you can see under this condition how much additional loss you would have. It's really quite striking. So there's the motivation to work with a good layout, a good component choice to minimize this loss. On the power loop, you can see there's also a benefit to reducing the loop inductance. Not quite as much benefit, but it's still there. It's still very much worth going into and looking at. And not just for the loss, but also for overshoot, for ringing. So you can see this is basically the same EPC GaN FET with two different layouts. In one, with more loop inductance, you'll see 70% overshoot. If you reduce this down to 0.4 nanohenry, you see quite a bit reduced overshoot on the waveform. And there, for comparison, is the common source inductance added in for reference. Okay, the impact of loop inductance. There's two loops to consider, the turn on and turn off. Sometimes there's separate outputs, sometimes not, but it is different loops from either the high side or down to the source. You'll see these here. So minimizing the inductance in the gate does pay off and is good to do. Some layout comparisons. The first one is very common, or at least was, with silicon MOSFETs. And you'll see basically all the power parts, the power loop on the top of the board. And you'll see a circle. And it looks kind of good because everything's right up there. But you can see the width of this loop, the width of the power loop relates to inductance. Next, another common layout is to put FETs on the top, a decoupling capacitor on the bottom. So you have a loop that instead of goes lateral, it's a vertical loop down to the bottom of the board and up to the top. The best one we found is this type of loop where you have all the power parts on the top, like the first example, except you use the first inner layer to complete the loop. So it's a very short loop viewed from above and from the side. And let's go into a comparison. First, the green, the lateral one. You can see the loop inductance is up there. Next is the vertical one, and you'll see it depends on the board thickness. So depending, it could be better, it could be worse, just depends on the board thickness. The third one, with using the first internal layer of the board, gives the best results, the lowest loop inductance. So that's a good way to do it. And there they are circled. So how do you get to that type of thing? Well, a good layout would be the placement of the FETs first, where you'd have the capacitors, where the plus would be on the bottom here, top FET and the bottom FET. And you can see some yellow vias here that would go back to the first inner layer and conduct the ground return path back up to the top of the capacitors. And there's examples of many EPC boards of this. You have the thinnest possible substrate between the top and the first inner layer. That can help a lot here too. You spread out the connections here on the top so you don't just have one or two vias, but spread them out so you have a nice wide current path. The ground return does not need to carry the full current, but it does need to minimize the inductance, be a nice path, this wide path. Okay, one thing comes up also is the current sense resistor. If you have a resistive shunt for measuring the current of the bottom FET, what do you do in this case? Well, there's a few things about here. One is you treat it about the same as decoupling capacitors. In other words, you have a few smaller ones in parallel. You'd really rather not use one big one. There's even possibilities of using like a wide connection in a short path to get the lowest possible inductance there. I should add here, there's at least two GaN gate drivers that allow you to separate the resistance to shunt out of the lower gate drive loop, which is nice. One from onsemi, one from ST. So those are something that could be worth considering also if you'd really rather not have those in the gate loop. First shunt layout. This is very similar to the one we just showed, where capacitors, top FET, bottom FET. In this case, here's the current sense resistors down here, and then going to the ground. So same general concept, just added resistors here. Okay, that's the end of that section. Next one, thermal, including thermal resistance comparisons of GaN FETs, heat spreading and heat sinks, and also EPC is a relatively new thermal calculator online, so we can discuss that briefly too. Okay, a comparison. Silicon MOSFETs are the red dots, GaN FETs in blue. So this is for device area and the resistance from the junction to the board. So this is board, the conduction of heat into the board. So they're about the same as silicon MOSFETs as a function of area. What's really interesting is over to the side here, the thermal resistance from the junction to the case, in other words, to the top, for putting a heat sink or a heat spreader. It's much better on the GaN FETs. You can see here it's down low. Even though silicon MOSFETs are bigger, even though they have things like metal tabs, you still find a much higher thermal resistance. So the conclusion here is that even though they're small chip scale devices, they can be adequately cooled, actually in many cases better. Let's get into this a little bit. Well, first, looking at the conduction into boards, there'll be three examples here. The first one's no vias. You'll see even with no vias, you can get some heat spreading by having big copper planes here. So everything is big. You can see, for example, even the gate has a big trace here, switch node, input, output, and so forth. That'll help spread some heat. To make it better, you can have vias on the side, tie the thermals of these big planes into other layers, including the bottom. That helps even more. The best one is vias under bump. Now it costs a little bit more, so some designs use them, some designs don't use them because of cost, but for technical performance, this is the best way to go. This takes the heat almost directly from the solder ball into the board and spreads it very well into the board in addition to the top layer. Some notes about the via construction. A via in pad plated over. I want to plate it over so the solder doesn't wick into here. And it's a nice flat area. So the wall thickness given here, hole diameter, annual ring, you can see in orange here, plated over, non-conductive filled. The question comes up, some APC engineers have looked and there's not much advantage to filled vias as far as we know. If you have another data point with newer fill, please let us know. Tinted on both sides of the board. So green solder mask, so tinted over so it doesn't show unless it's intended to be exposed. This is used for under pump and close to component pads. Just up to 2 ounces. Okay, now skipping to top cooling, which from the graph we saw, that is the, this will always conduct to the bottom, also conduct to the top. So how would you attach a heat sink to a GaN FET? Well, a nice little easy way to do it is to put some spacers in. These are actually threaded hole surface mount spacers. They can be put in. As it shows here, it's about 1 millimeter spacing from the board to the top here. A TIM, a thermal interface material, which would go on top of the FETs to conduct heat through the gap between the top of the FET and the heat sink. And the heat sink over top with some screws to screw it down. This has the advantage of a good thermal contact without having mechanical stress going right from the heat sink right onto the FETs. It's a cross section. You'll see the heat lines in dark red are the more primary path of the heat. You'll see smaller ones, smaller conduction paths. You see a capacitor in here. That's not bad because the capacitor can act like a bridge to take some heat from the board into the heatsink, which is good. So that's not a problem to keep this all clear. Other parts to fill up the gap is actually good. Heat spreading. It's a little bit different, heat spread and heat sinking. Heat spreading, as it implies, can help take a relatively small EPC GaN FET and increase the area where the heat will be conducted through copper. Effectively increases the thermal area. Heat sinking can be used with heat spreaders or alone. That increases surface area, especially when there's airflow. The surface area of the heat sink for better cooling. So as I mentioned, it could be either combined or independent. Again, heat still does flow into the PCB. Okay, on the left is a full thermal model of 2 FETs, P1, P2, and all the different paths and the different values that you would have to use to calculate this, which can appear a bit daunting. But what's really nice is EPC does have a thermal calculator online. Here's a diagram from it. So you can select either 1 FET or 2 FETs. You can select vias under the pads or not, a heat spreader or heat sink or not. And beyond just the thermal gap, you can determine whether you want to have gap filler to further conduct heat. Sometimes it makes a nice difference, but with larger FETs, it doesn't do much. But you can see for yourself as you go through that whether how things are working there. So in other words, you can skip the model, go directly to putting the circuit as you'd like it mechanically and thermally. And then there's a box with the result summary. under the conditions stated, in this case, 25 degrees C, what's the temperature rise and what's the junction temperature of the FETs? And I think that's it. So as a summary, maybe Renee can go through this too. There's 3 more talks coming.
Oh, yeah, I'm just trying to find my video. Okay.
Oh,
There you
sorry.
go. Thank you, Brian. Yeah, so there are 3 more webinars in the series. You can see the schedule here. The next one up is GaN device reliability. But first, we are going to just go through some of the questions that came in, and you can still continue to submit your questions via the Q&A function at the bottom of your screen. But the first one, Brian, is on slide 13. The question is I guess what you were showing, is that similar to interleaving?
Slide 15. Let's see if I can. There's so many build outs here in the slides. The question is this similar to interleaving? Not sure I understand the question. There's 2 outputs, a pull up and a pull down.
Okay. Well,
yeah, I'm sorry. If you have somebody, whoever wrote
if you
that
want to
question,
clarify the question,
yeah.
we can.
Yeah, I'm sorry. I just don't
We can
understand.
try to address it. No problem.
Yeah.
On slide 37, you're showing capacitors, and the question is, well, the statement is that the area will get very hot. Capacitors are usually rated from 85 to 125 degrees. So I guess the question is that an issue?
It's something good to check into. Yeah. And in a lot of cases, even though EPC FETs are rated higher, a lot of designers choose to do 125 degrees C max on the junction and keep the heat sink noticeably cooler. So that is a good point. Yeah, to keep the capacitors in acceptable heat range. Yeah. If that does become a point, another way which isn't shown here, instead of a capacitor, there are aluminum heat conduction devices that can be bought, or even just cheap resistors can be put here, which are that can take high current. So that's an alternate path to taking heat from the board up into the heat sink, and maybe, like you implied, having the capacitor not right in that area.
Okay, there's a couple of questions about access to the slides. So I believe within 24 to 48 hours of the end of the webinar, you'll receive an email with a link to the recording, and I believe the slide deck is also included in that as well. If it's not, you can always send an email to info@epc-co.com, and we can get that for you. Okay. Question in the graphs where GaN FETs are compared to silicon FETs, are the silicon FETs the best for the parameter compared, or just the general state of the industry?
Something like this one, tried to include the best ones we knew of at the time these were made. This one does show quite a variation, but yeah, we believe that we're showing the best ones available there.
Okay. On slide 13, why should the circuit with the diode be avoided?
Yeah, that's a good question. I know what you mean. Why should this one be avoided? I think the question is that a lot of people use it successfully. I've done that too, like with silicon MOSFETs. You have 2 different resistors here, a good turn on and a reduced resistance for even better turn off. So why should you avoid that? It does come down to the gate threshold. And also, we've also seen, because of the speeds, diodes aren't diodes. Even a Schottky diode, one of the EPC application engineers found that due to ESD structures, there's a little bit of reverse recovery in a so-called Schottky diode, and some of the small signal ones he looked at. So coming down to not just the voltage, but also unintended parasitics that aren't really specified can cause some odd operation, and we've seen it. So yeah, you're certainly welcome to try it, but yeah, it is better just a single resistor in our experience, just to avoid the possibility of something happening due to greater complexity.
Okay, another question. In some applications, it is desired to slow down the transition to control inrush current. Can a Miller capacitance be added between drain and gate to slow down the switching? And if not, what method would you recommend?
Between drain and gate, yeah, that's probably not, because that would put potentially more charge right onto the gate. To slow it down, let's see, a few ways to do that. Probably through gate driving is good. I'm not sure I'm answering this very well, but whoever asked the question, if you want to contact me directly, that'd be great. I think you're saying for inrush, say for example, maybe with a load switch or something that switches in, you'd rather not have so much current. Either through current sensing or through the gate drive itself. But again, yeah, putting a resistor or a capacitor, I'll show it here, like from this point, from the drain down to the gate. Yeah, that's, you might be on the wrong side of the Miller capacitance and actually cause it to unintendedly turn on under fast switching.
Okay. All right. The next one is, in your layout slide, you showed how to minimize power loop inductance by using the next available layer to conduct current. Could you use a similar strategy to minimize your gate loop inductance?
Yes. Here's a gate loop induct. That's a very good question. That wasn't really covered here. But in general, taking a line that's relatively wide, not for current, but just for low inductance, coming from the driver over to the transistor, say on the top layer, and then having underneath the source coming back. So the first layer just underneath it, for example, because that is the reference of this one. On the top one, you would have the source, which is the switch node, which to some people seems kind of odd because that could be a noisy reference, but that is the reference for the top gate driver. So having something like the resistor on the top going to the gate, and then having the inner layer with it on its reference would be the switch node coming back to the driver. Yes, that'll help with overall performance and also noise too. So yeah, good point, good question.
Okay, another question. Did you consider the power dissipation trade-off between adding a copper return path under the switch node versus the extra capacitive loading between the switch node and return?
Oh, I think with these, yeah, we've seen it actually work. If there's another one that's a little bit better here, I guess this is good. I think the question is, once again, adding copper below the switch node, which in effect creates capacitance on the switch node. I guess there's two answers. One is the current. Typically, there's an inductor there, so the current doesn't change right away on the switch node. But I think you meant more voltage. So having the switch node, which is between the FETs, let's see over here, coming right out. Yes, I think it does work. We did find it works better to have the switch node there, because even with the ground, the capacitance didn't seem to affect it as much.
Okay.
Seems like the inductance is more of an issue and some of the losses we saw versus the other one.
Can you explain internal vertical layout once again? If we keep a bootstrap supply, it will take time to charge capacitors, which will slow down the higher switch gate driver, correct?
The internal vertical. This shows the power loop, not the gate loop. But yeah, again, it's basically putting all the parts on the top in a row using the first inner layer. The second part of the question is related to the gate drive. Is that right?
Let me go back and find it.
I'm sorry.
Yes, no, it's fine. If we keep a bootstrap supply, it will charge capacitors, which will slow down the higher switch gate drive, right?
Maybe the first pulse, but with the bootstrap capacitor and so forth, once the capacitor is charged up for the upper gate drive, the speed of that charging up and so forth doesn't really matter that much unless it's a very extreme duty cycle. But I don't think we've really have seen that show up as an issue.
Okay. Is there a particular gate driver that will perform best for matching gate charge and gate capacitance for top speed?
I would say going back to the, let's see, wherever I put those, the gate drivers, back up here. A lot of these are designed for different types of things. The fastest one we know about is this one, the LMG 1020 single gate driver. So for the fastest operation and best switching, this would be it. Now, I mean, there's some drawbacks. You know, it doesn't have a built-in LDO, so you have to provide your own 5 volts and so forth. As far as half-bridge ones, let's see, the fastest one might be this one, the LMG 1210. But, you know, it's 200 volts. If you don't need 200 volts, it's a trade-off. Looking at these 3 here, the pin-compatible ones, you can look and see, well, they're not really for that high of speed operation in terms of megahertz, but they do switch fast. Also, there are many application notes EPC has to make these operate efficiently up in the megahertz, say above 6 megahertz even, by bypassing an internal slow diode that's in all of these with an external circuit. So it really depends on what you need. I think that's the best quick answer is the maybe this one, the LMG 1210, LMG 1020 as far as the fastest ones.
Where is the best place to put a current sense transformer in the half bridge?
Current sense transformer in the half bridge. I don't really know. It can be, if you have a favorite place to put it with the silicon MOSFETs, because of the array of gate drivers now, you might be able to do the same thing. In other words, if you prefer a gate current transformer or current sense resistor in the bottom, there are ways to isolate that from the bottom gate drive loop. Many controllers use the inductor, which could be also a transformer to measure, and that's pretty benign to the GaN FETs. So I'd say in the switch node somewhere is probably the best place for it because it gives you the widest array of gate drivers without affecting the power loop and right near the FETs.
Okay.
But yeah, feel free to write in with specific requirements or a schematic or so forth.
All right. Can GaN semiconductors be manufactured in a sustainable way? I would say yes.
Yeah, I would say yes too. It's kind of outside my expertise, and
yeah.
I mean that's a very good question. One thing that's sustainable is just simply the size. I mean, my goodness, they're so tiny that it takes a whole lot less wafer to make a bunch of GaN FETs. One of our best-selling ones is 0.9 by 0.9 millimeters. So you could say, you know, that's a good start. There's a lot less materials there's a lot less hazardous materials used, I believe, in GaN FETs versus silicon MOSFETs. They aren't doped, they're layers they're put on top. So I don't think arsenic and other things are used. Somebody correct me if I'm wrong, but I think overall it is. The element gallium I looked up years ago, and it seems like it's biologically inert from what I could read about it. So I think it's pretty, as far as we know.
If that's what I meant by sustainable. If it meant
Yeah.
reliability, we have an entire webinar on that in 2 weeks. We can talk about reliability.
Yeah.
Yeah. Okay. One more. How do you probe a current sense resistor to know the exact current flowing in a half bridge circuit?
Down and find one. How do you probe it? Find. Typically, a lot of here we go. Typically, a controller or some current sense amplifier will be here. If you have an amplifier, that's great because it'll be connected. You can look at the output of the amplifier and see a nice big signal that'll be related to what actually it is there. So if you pick the or just with an oscilloscope, if you can have a good probe, put the ground right on the bottom of the probe, and the ground and the actual probe itself right on the top of these here, ground and top, then that should give a real good idea of the current going through there. I hope that's the question that was asked.
Okay. All right. So we're right up here till about the end. So I'm just going to thank everybody for attending today's webinar, and thank you, Brian, for hosting, presenting. If you do have additional, oh, I'm sorry, one more question came in. Let's just get to it. What is the best way to dampen the ringing on the gate node, especially if there is a single signal? That was difficult for me to say. Single signal. Yeah.
Okay. Yeah, there are very many excellent gate drivers and controllers have a single signal output. I think that's what it means, just a single, not a pull down, but combined. So what's the best way to do that? The best way to do that is start with a good layout, just have them close together. But beyond that, pick the resistor to minimize the ringing. Look at it in both directions. But err a little bit on the side of a slight bit of ringing won't be bad. For example, if it's a 5-volt gate driver and it rings up to say 5.5 or even 5 3/4, that's not bad. So just as your design would like, but keeping the turn off is probably more important. You don't want it to ring and potentially turn back on. So I prioritize turning off ringing over turn on ringing.
Okay. All right. So that was the last question. Thank you, everybody. If you think of other questions, please feel free to reach out to us at info@epc-co.com and we'll get them answered for you. As I mentioned, you will receive a follow-up email within 24 to 48 hours, which has a link to view a recording of today's webinar. And I believe the slide set is also included in that as well. And then lastly, just be sure to register and attend the remaining installments of the Summer of GaN webinar series. Our next one is on August 3rd, where our CEO and co-founder, Alex Lido, will discuss the extensive reliability testing that's been done and the behavior of GaN devices over a wide range of stress conditions and applications. You can visit our website at epc-co.com for more information and to register. Thank you for joining us today and have a great rest of your day. Thanks again, Brian.
Thank you all. Bye.
Bye.